Hello guys, so before I get started, let me go ahead and start my timer. All right, so I've started the timer to reflect how much time we have in class. So let me go ahead and get started. So, move my little thing. Okay, so happy Thursday, guys. Unfortunately, I'm not able to be there with you guys, but I will be back tomorrow. So on our ready check, you should have the Newton's Laws foldable. You should have the Laws of Motion handout. Okay, so Newton's Laws foldable was this one. Okay, Laws of Motion handout. Calculating force, mass, and acceleration. And I also put out loose leaf paper because you may need that. Well, you most likely will. You can write on the back your calculations. I would just make sure I had a piece of loose leaf paper as well. Okay. And then you will also need a calculator. Okay. So let's go ahead and get started. So today we are going to review the first and third laws of motion. And then we're going to learn how to calculate force, mass, and acceleration and apply that to Newton's second law. Tomorrow, we're going to continue with calculating and interpreting Newton's second law. Upcoming events, Ranger Showcase is on the 27th. And today is February, move this down, yes, February the 20th, 2020. My expectations for the day. What does Miss Harrell want to see today? Sit in your assigned seat. If you are anywhere else right now, please move right now. Okay? I have already given my substitute a seating chart. She knows where you're supposed to sit. Okay? So I'm going to give you a second to think about the choice you're making. And I've also asked her to snap a photo of the class and email it to me at my email address that I provided on my desk. Do not sit anywhere else. Please follow directions the first time they're given. There's no talking at all. The only students that are allowed to talk are my students who need language supports, and they know who they are. And I've already given her those names. And if you don't know if it's you, then it's not you. Okay. Do not disrespect my substitute under any circumstances, or I'm going to deal with your bald head self tomorrow with that fill in the blank good old test. So please be respectful to my substitute. She's taken time out of her day to come and be with you guys. So please be respectful and do whatever she asks you to do. Thank you guys. So let's go ahead and get started. Let's start with our daily recap. So we started off this unit learning about the first law of motion, which just says an object at rest stays at rest. An object in motion stays in motion unless acted on by an unbalanced force. Okay. So this is Newton's first law, and most of the examples that I gave were moving at constant speed, moving at all. The only thing that's going to stop you is an unbalanced force. So, like gravity and friction oppose movement. If I pick up my pen was at rest until I applied an unbalanced force and picked it up. And in order for that to happen, I must overcome the object's inertia, which is directly related to its mass. The more mass it has, the more it resists a change in motion. Okay, so I have to overcome that in order to move it. Here's another example of Newton's first law. Objects in motion stay in motion. Pretty much objects want to keep doing whatever it is they're doing. If they're at rest, they want to stay at rest. If they're moving, they want to keep moving. So the guys on the motorcycle, he hits a brick wall and he keeps going. Okay, the motorcycle was stopped by the brick wall, but the body, the person, wants to keep moving at that same speed. So he's going to keep moving until an unbalanced force stops him, which is most likely going to be the pavement. Here's another example of Newton's first law. Okay, so this is on the left side, you see someone driving, and then on the right side, you see them slamming on brakes. So whenever the brakes are applied, the person wants to keep moving forward. Okay, And that's because the object is in motion. I did explain yesterday, if you were in a car riding at 70 miles per hour, your body is also moving at 70 miles per hour. And you want to keep doing whatever you're doing. You want to stay in motion. The unbalanced force is the seatbelt that stops you from continuing to move. All right. Then we went to the third law. Okay. Newton's third law says that for every action, there is an equal and opposite reaction. So we did our balloon demo yesterday in the class. The air pushed back out of the balloon, but the balloon went forward. They must be opposite. Okay. It can't be I stand behind someone and I push them. I'm pushing forward and the person is also moving forward. That's not equal and opposite. Okay, here's a swimmer. This is one that we talked about as well. Notice that she's pushing off on the wall to get a better acceleration or higher acceleration. And also remember that we talked about the blocks for track. Okay, so a lot of students shared their experiences that they use that block to get a good start. They want to increase their acceleration as they're coming off of the block. Okay, now let's move into our last law. I know we did them out of order. We didn't do first, second, third. We did first, third, second. And I waited on second because it involves calculations. And I know that it's not our favorite thing to do. So here's a joke from Newton. He is the science driver. And the person is saying, it stopped because we run out of gas, Sir Newton. And Newton says, but we're moving. We should have kept going based upon his law of inertia. Okay, I made a funny. I know you didn't laugh, but it's all right. So here we go. Force equals mass times acceleration. And we're going to get our triangle today and we're going to do some calculations. If you look at the images, you can see that the ball on the left is a lot more massive. It's 10 times as massive as the ball on the right. You can see that on the left, he is exerting a large amount of force to cause that ball to accelerate. On the right, he only has to use a small amount of force because the mass is a lot smaller. Okay. So go ahead and get your foldable. So you need to get this one. Okay. 1 second. Let me tell my kid to take. Okay. So we're going to fold this like a brochure. If you look at the one on there, I'm going to fold mine the best I can. I left my hover camera at school, so I couldn't record it on a flat surface. Okay, so it's pretty much going to be, oh Jesus, like this. All right, so I folded one page in and the other page in and made a brochure. Go ahead and fold it down. Okay, so I'm folding mine down on a notebook here. Give me 1 second. All right, now I am ready to roll. So let's go. All right, Newton's first law, and that is going to be our first page right here. You can see that it has the person with the bike, and I'm going to write as you're writing so that I can make sure that you have enough time to get it done. So Newton's first law is also known as the law of inertia. The law of inertia just means that objects are lazy. They want to keep doing what they're doing. An object at rest will stay at rest unless acted on by an unbalanced force. My braces are getting on my nerves. Jesus Christ. An object in motion will stay at motion in the same speed or at the same speed and direction unless acted on by an outside force. I'm gonna move this as far as I can. All right. So this is just a fancy way of saying objects want to keep doing whatever they're doing. So now I'm going to go ahead and fill in. And I'm checking motion. Well, that's not what I meant to do. I'll turn off low power mode. Okay. Sorry, guys. All right, I'm back. All right. Object in motion will stay at motion in the same speed and direction unless acted on by an outside force. And here's our example. Okay, the guy's riding his bike. He's riding just fine. He hits something. He goes flying and also does the bike. But he accelerates faster than the bike, further than the bike, because he wants to keep moving. Nothing has stopped him yet. It's only stopped the bike. Okay, so let me fill that back in. Sorry, guys. And if you didn't finish it, don't worry. All right, here's our example. All right, the top balloon will continue in motion until an outside force stops it, and the second balloon is at rest. Okay. And we will fill in the keywords together tomorrow. Let's go to our second law. Newton's second law is also known as force equals mass times acceleration. The acceleration is produced when a force is acted on a mass. The greater the mass, the greater the force needed to move that object. Okay, so we also we looked at two individuals, one small, one large, and we talked about how much force they would both need to move the two kids in the rolling chair. So I'm going to go ahead and fill in. Okay, so there's our example. I'm a guy hitting two separate types of balls. The first ball accelerates a lot faster because it has a lower mass. And the second ball you can see is a larger size. So, okay. So it does not accelerate as far because it requires a lot more force for that same acceleration. The person is hitting the ball with the same force. All right. What here are our examples. The top balloon is like the balloon that I blew up in the class. Okay, so there's an action and reaction. The action forces the air blowing out. The reaction is the balloon moving forward. Okay, if you look at the top balloon, it has a greater mass. Therefore, I need to blow it up a lot more. That is the source of the force for this one in order for it to accelerate. And on the bottom one, it has a smaller mass, so it doesn't take as much force to accelerate. So the more mass it has, the greater the force needed, and the less mass that it has, the smaller the force needed. All right. And lastly is our third law. Newton's third law is also known as the law of action reaction. For every action, there's an equal and opposite reaction. Okay. So our examples for this one is the rocket. So we learned that the combustion and gas from the rocket push down and the rocket goes up. And then we did the balloon demo, the balloon rocket actually in class. I blew the balloon up, the air came out of the back, and the balloon moved forward. Okay, there's nothing to write here because action and reaction are already done. Let's move on to our next handout that says Newton's laws of motion. This one looks just like the one that's on the screen. This is going to be like a I do, you do type of activity. So let's get started. First law of motion. That means these four questions all deal with inertia and Newton's first law. Newton's first law of motion states that an object at rest tends to stay at rest, and an object in motion tends to stay in motion with the same speed and in the same direction unless acted upon by an unbalanced force. This is also known as inertia. We're going to read each description. Well, I'm going to do two, then you're going to do two. And then we're going to answer the questions. Number one, Jonathan wants to put ketchup on his burger. He turns the ketchup bottle at an angle towards his plate and smacks the bottom of the bottle until the ketchup comes out. What is the unbalanced force? And how does inertia affect the ketchup in the bottle? Well, the unbalanced force is any force that causes a change in motion. When he turns the ketchup bottle at an angle and smacks it, that is the unbalanced force. Okay, the ketchup bottle was at rest. He turns it, that's changing direction. That is a change in motion, that's unbalanced. And then he smacks it. Okay, so he's trying to get the ketchup to flow out. Well, how does inertia affect the ketchup in the bottle? The ketchup keeps moving. The ketchup keeps moving out. So I'm going to fill in. My dog is cutting up. Okay, gonna move this up. The Jacksons are driving to the mall when a car in front of theirs slams on brakes. Two. Okay, so they're both slamming on brakes. The car slams on brakes in front of them, and then the Jacksons' car slams on brakes as well. Everyone is wearing their seatbelts, which stops them from being thrown forward in the car. What is the unbalanced force? Well, the brakes is one unbalanced force. Okay, them stopping the car, right? So the brakes or the seatbelt stopping them can be an unbalanced force. I chose the seatbelt stopping them. How does inertia affect each person in the Jackson's car? Well, we know that objects in motion want to stay in motion. Objects are lazy, they want to keep doing whatever they're doing. So, how does that affect the Jacksons? Well, the Jacksons are going to keep moving forward until that seatbelt, that unbalanced force, stops them. So, when the car slams on brakes, the Jacksons continue to move forward until the unbalanced force stops them, the seatbelt. I'm just filling in. Okay. Right. So you're going to do these independently here in a moment. Let me move to the second law. Newton's second law of motion states that acceleration is produced when a force acts on a mass. The greater the mass of the object to be accelerated, the greater amount of force needed to accelerate that object, which means the more mass, the more massive an object is, the more force I need to apply. Each of the following situations demonstrates Newton's second law. Describe how the difference in mass will affect the acceleration in each situation. I'm going to do number 5 with you. So number 5 starts here, but you actually answer on the back. Sorry about that. Amy weighs 78 pounds and her dad weighs 187 pounds. They are roller skating. Amy challenges her dad to a race. They stand waiting at the starting line and her dad yells go. Well, the only thing that we have to think about here is who has the lighter mass. Amy. So Amy is going to accelerate faster. Okay. So my answer that I decided was Amy weighs less than her dad. Therefore, when the race starts, she will accelerate more, or we can also say she will accelerate faster. All right. You're going to be doing number 6 and 7 independently here in a second. And then Newton's third law, which is very simple. Newton's third law states that for every action, there is a separate but equal, my preference is equal and opposite reaction. For for each situation, describe the action and the reaction force. Two children on roller skates stand facing each other. The child on the right puts her arms out and then pushes away from her partner. So there's two people that are hand in hand, okay? And they both push off of each other. The action force is the child that pushes, okay? The reaction force is the other child pushes back with the same force and they both move backwards, just like what we saw yesterday with the guy in the chair and the cheerleader with the smaller mass in the chair. Okay, so this is action reaction. The action was the child pushes. Okay, they both push to each other, but they both are going to move backwards. Okay, so the action force is the actual push, and then the reaction is them moving backwards. All right, so you can go ahead and finish numbers 3, 4, 6, 7, 9, and 10. Before you do that, how much time I have left. Okay, I have 22 minutes, so that's fine. So what I'm going to do is I am going to go ahead and complete mine. Okay, and when I'm done, we're going to pick back up with the next activity. So I'll be here while you complete the numbers that we did not. Okay, four pretty simple. They both trip or almost trip. Okay, so I'm done with that one. So we're going to move forward with our calculating here in a second, right? So we're only going to do a few of those. If you're still working on this one, please finish it up and set it aside. Let me check my time again. Right, so it only took me a couple of minutes. So I'll give you a few more minutes and then we're going to pick back up. So I'll give you about 2 or 3 more minutes and then we're going to move on to our calculating practice. That sucked. Now I'm going to be thirsty. Sorry about the noise. My son has taken over my living room. He's playing Fortnite, so that's why I'm in my room doing this video. All right, so let's move on to this one. Put on PowerPoint. All right. Calculating force, mass, and acceleration, and it has our triangle at the top. Right? Let's take a look. Plug in the given values for force, mass, and acceleration to solve. Remember that mass is in kilograms, force is in newtons, and acceleration is in meters per second. So if we look at our triangle at the top, I actually draw it a little bit bigger on my paper. Just to reinforce what we did with speed. So the S is not in the bottom left like how it was in speed. So that's where mass is. Because remember, if they're side by side, you're going to multiply them. Let's see, maybe not. It looks like a big blur. Okay, whatever. The triangle is at the top, so it is right here. And remember, if you want to solve for force, then you cover up the F, and then you do m times acceleration. If you want to solve for mass, then you can cover up mass with your finger, of course, and then you divide F over A. And then if you want to solve for acceleration, you cover up A, and then you do F over M. So I'll write those out, and you can write those on your paper. So force equals M times A. M is equal to F over A, okay? And then A is equal to F over M. So when I go to the next screen, you will not be able to see those again. So please go ahead and copy them on your paper somewhere so that you can easily work through the problems. So if you don't need to copy it, it's okay. Just remember that all you have to do is cover up whatever you're solving for, and it'll leave, the other two variables that you're working with. And if they're above or below each other, that you're going to divide. And if they're side by side, like M and A, you're going to multiply. Okay. So let's go ahead and get started. I'm going to write on the screen, and then I'm going to move forward with you doing it on your own. You are required to show your work. That's why I encourage you to get a scratch sheet of paper. I left my hover cam, so I can't actually show you on my paper. Okay. So for number 1, it says how much force is needed to accelerate a 66 kilogram skier at 2 meters per second squared. Well, I'm looking for force, so my formula is F equals M times A. You must write the formula first. And I'm looking for force, so that's a question mark. For force, I don't know what that is. But I know that my mass is 66. Remember, mass is in kilograms. And I know that my acceleration is 2. Okay, so now I'm going to move forward to plugging in my variables. You must do it just like this with your steps. Okay, so F is equal to 66 times 2, and that is going to be measured in newtons. So let's see what we got. Right, so our answer is 132 newtons, and I'm going to ask that you put a box around it so that when I am checking it, I can easily get the information or your answers actually. Let's move up here to number 2. What is the force? What didn't work out? What is the force on a 1,000-kilogram elevator that is falling freely at the speed of gravity, 9.8 meters per second squared? So I'm going to write my equation. I'm looking for force again, so I know I need to use this equation. So force is equal to mass times acceleration. F, I don't know. Mass is 1,000 and acceleration is 9.8. So what I'm going to be doing is mass times acceleration. So I did 1,000 times 9.8. So F is equal to 1,000 times 9.8. And then that is equal to 9,800 newtons. Okay, force is measured in newtons. Right? Now, number 3 says, what is the acceleration? Oh, come on. Okay. What is the acceleration of a 50 kilogram object being pushed with a force of 500 newtons? So this time I'm solving for acceleration. Great. Okay, so if I shade in A, I know that I need to do F over M, which is just what I specified right here. So my formula is A equals force divided by mass. I can't write too low because the screen keeps stopping me. So let me try this. 1 second. I'm going to write it a little bit smaller. Okay, so force, acceleration equals force over mass. So it's not, there it is. Okay, sorry, it's a little ugly. All right, so my acceleration is equal to my force, 500, okay, divided by my mass, which is 50, which is equal to 10. Now it says that acceleration is in meters per second squared, so my units are 10 meters per second squared. So we've found force for 2 problems, and we've also found acceleration. The only other thing left is to find mass, and then we should be able to do all of the problems. So let's go to number 4, and I'm going to rewrite the triangle just because it's not here. Okay, and you already have it on your paper, and you don't have to use it unless you want to. Okay. The mass of a large car is 1,000 kilograms. How much force would be required to accelerate the car at a rate of 3 meters per second squared? Once again, I am solving for force. So force is equal to mass times acceleration. Okay, my variables, force, I don't know what that is. The mass is 1,000. And then the acceleration is 3. Okay, so my formula is F equals 1,000 times 3. Okay, and 1,000 times 3 is simply 3,000. And I'm looking for force, so I know that that is in newtons. Okay. For number 5, a 50 kilogram skater, 50 kilogram is a mass, pushed by a friend accelerates at 5 meters per second squared. How much force did the friend apply? Well, I'm solving for force, so F equals M times A. Here go my variables. Force, I do not know. I know that my friend had a mass of 50 kilograms, of the skater actually, and then he or she accelerated at 5 meters per second squared. Okay, so my formula is F equals M times A. Oh, I already wrote that. What am I doing? take that off. I meant to say, plug in my variables. F would equal to 50 times 5. Therefore, F equals 250 newtons because it is force. Okay. And then for number 6, a force of 250 newtons is applied to an object that accelerates at a rate of 5 meters per second squared. What is the object's mass? Well, if I scratch out mass right here, I know that I need to do F over A. Okay, so I'm solving for mass now. So mass is equal to force over acceleration. My mass, I do not know. My force is 250. And then my acceleration is 5. Okay, so now all I need to do is set up my equation. All right, so M is equal to my force, which is going to be 250 divided by 5. And therefore, the mass of my object had to be 50 kilograms. Don't forget your units. Okay. So that is half of the paper done, which is about 6 minutes. I want you to complete as many problems as you can in that 6 minutes, and I'm going to work problems as well right along with you, so I know how many problems you should have had completed, if not all of them. So we're on to number 7, and when the timer goes off, I will regroup again with you. On number 7, you have to solve 2 different equations, one for the first ball and then one for the second. Some scratch paper. For number 7, you're solving for mass. So cover up your M, and then you should see that the equation is F over A. Don't forget your units, guys. Number 11 is really good. You have to calculate the net force first. So friction is opposing it. So 40 minus 8 would be 32 as the force. All right. So I just finished. Our timer is about to run out. So depending on the class period, some of us have 50 minutes or 52-minute class periods. I have left you with 2 to 4 minutes of packing up and cleaning up. Um, you are going to turn both of the papers into my substitute. Okay, so this one and this one. You are going to keep the brochure. Please bring it back as you do have assignments on this. Bring this back tomorrow. Matter of fact, give everything to my sub. Y'all not to be trusted. Turn in everything. All right. Have a great day. I will see you tomorrow.